for a moment about cola. Delicious, profitable, remarkably versatile. Now, we're all familiar with this delicious beverage, which is a recreational beverage of choice for billions, and probably with some of the myths associated with it as well. A quick search of the internet will uncover shocking claims that cola can be used to clean blood stains, to remove rust from chrome car bumpers, and even that it has the remarkable ability to dissolve a human tooth or even a whole steak in startlingly short time frames. Most of these claims can be attributed to the addition of just one simple ingredient, phosphoric acid, to the hallmark formulas of such popular brands as Coke, Pepsi, and others. Phosphoric acid, it's a scary sounding chemical, isn't it? But the truth is, these beverages lack any special power to do the kinds of damage that are being suggested in urban folklore and online videos espousing the ideas I just mentioned. Make no mistake though, acids and bases do have remarkable chemical power. They're largely responsible for the weathering of certain types of rock in the environment. They are common ingredients in the foods we eat every day. And they even help to keep your own body's chemistry running smoothly. What is so remarkable about acids, beyond their influence in nature, medicine, and engineering, is that they exercise this influence using some of the smallest ions that the universe has to offer. This lecture is dedicated to beginning to understand exactly what's meant by the terms acid and base, and why so much confusion seems to exist surrounding their effects on people and our environment. So let's begin our discussion of acid-base chemistry. The ancient Greek culture was already very familiar with some of the acids that you might have in your kitchen right now. The classic example, of course, is this compound, vinegar, also known as acetic acid. In fact, this acid is so common in nature that it was known to cultures so ancient that mankind's first discovery of this chemical likely predates history. The term acid finds its roots in Latin, where the term acidus literally means sour. It's a reflection of early Western civilizations lumping together of anything with a sour taste in a single category of substances, then giving it the only logical name, considering the classification. So, as long ago as the Roman Empire, people were referring to acids, only knowing that they were a class of materials that had a sour taste. As oversimplified as this may seem to us today, it's understandable that ancient cultures would group materials in this way, since they really had no other means of categorizing compounds and substances. Remember, the periodic table was still about 2,000 years away from being developed. Now, another class of compounds also became well known to cultures like ancient Rome. When objects were burned and their residue or ashes collected, they often mixed with water to create slippery substances. The term alkali, still used to describe bases by modern chemists, actually finds its origins in the Arabic term for calcined ashes. Now, by calcined ashes, I mean the remnants of a fire, usually of plants. Now, ancient peoples discovered that adding a little bit of water to the ashes of wood fires created a slippery, bitter-tasting material. And this became the first working definition of the term alkaline. It's funny how the practice of tasting chemicals once was considered a proper analytical technique. One could say that the human tongue was our very first chemical analysis instrument. Of course, today we have safer ways of testing to see if something is an acid or a base. But a real discussion of the chemical causes of these interesting properties of acids and alkalis, which we now call bases, would have to wait until the Great Awakening of chemistry in 18th century Europe. It was a few very familiar fathers of modern chemistry who decided to take their characterization beyond how these substances tasted on the tongue or felt on the fingers. Instead, they tackled the question of what exactly makes an acid and a base in chemical terms. The real discussion began with Lavoisier, who, with the luxury of his accurate knowledge of certain elements and methods for acquiring pure oxygen, was able to conduct experiments on compounds known to contain this common element. Since he found it in so many compounds historically classified as acids, Lavoisier reached the conclusion that oxygen was the key component of an acid, the essential element which endows acids with their characteristic properties. He reached this conclusion because the acids available to him included compounds like sulfuric acid, nitric acid, and phosphoric acid. All of these compounds can be made by adding the oxides of the associated nonmetals to water. So naturally, he saw fit to advance the theory that it was oxygen which drove their chemistry. He even went so far as to choose the name oxygen, literally translating to acid maker. But Lavoisier was wrong on this one. Lavoisier's theory that oxygen was the cause of acidic properties didn't stand long. It was toppled in very short order by the Englishman Sir Humphrey Davy. Davy noted, just a few decades after Lavoisier's assertions about oxygen, that the compounds hydrogen chloride, hydrogen sulfide, and hydrogen telluride all appeared to have acidic properties, yet no amount of effort on his part could produce or detect oxygen from any of these compounds. Now, that stands clearly to reason, since today we know that none of these compounds contain oxygen at all. But Davy was just beginning to discover this fact, and he knew now that oxygen could not be the crucial element for acidity. But if oxygen wasn't, then what was? All of Davy's new acids reacted with metals to produce hydrogen gas, which was unmistakable even in his day. Simply collecting the forming gas and exposing it to a flame to produce water was a positive test for hydrogen. And he noticed it forming again and again as a variety of acids reacted with metals. So it would appear that his results, while ruling out oxygen, made hydrogen look more and more like an essential element for acidity. But there are countless hydrogen-containing compounds that are not acidic. Compounds like methane, that contained hydrogen, but it showed no acidic behavior whatsoever. So Davy had taken a step in the right direction, identifying hydrogen as the essence of acidity, yet there had to be more to the story. The conclusion to the story would have to wait another half-century for Svante Arrhenius. Now recall that Arrhenius made a name for himself early in his career by demonstrating that many compounds become ionized in solution. This was a linchpin idea for explaining the colligative properties of solutions, in which we had to estimate the Van Hoff factor for ionic compounds because of their tendency to separate into ions in solution. Arrhenius' theory of ionization also explains why certain hydrogen-containing compounds are acidic, while others are not. The key question is not, does the compound have hydrogen? The key question is, can that hydrogen be removed as an ion? Arrhenius realized that acidic compounds were those which contributed hydrogen ions to solution when dissolved. And it was this key epiphany that dissolved protons equated to acidic properties that truly ignited our understanding of what acids are. He also applied his theory to bases, defining them as compounds which ionized to produce a hydroxide ion when dissolved in water. Common examples of this are potassium hydroxide and sodium hydroxide, compounds found in the substance commonly known as lye. The hydration of metal oxides, like sodium and potassium oxides found in ashes of a wood fire, produces that sodium hydroxide and potassium hydroxide. These are both ionic compounds capable of ionizing to release their hydroxide ions into solution when dissolved. Now, we call this classification system, in which acids are proton donors and bases are hydroxide ion donors, the Arrhenius definition of acids and bases. But even Arrhenius' Nobel Prize-winning work on ionization wasn't enough to explain it all. Yet another very simple compound defied explanation using Arrhenius' system. Ammonia is well known to create basic solutions when dissolved in water. Let's think about that for a moment. Dissolving NH3 in water produces OH- ions like a base. The obvious problem here is that ammonia contains no oxygen. This is a serious flaw in the Arrhenius definition of bases. How can ammonia produce hydroxide ions? It doesn't have the right elemental makeup. It's a flaw that didn't go undetected in the scientific community, and it didn't take long for two researchers to independently modify the Arrhenius definition of a base to account for this observation. You see, Arrhenius failed to consider the solvent in his acid-base theory. He simply assumed that water was an inert substance, only there to solvate ions produced by the acid or base itself as it ionized. In that respect, Arrhenius could not have been more wrong. In 1923, Johannes Nicolaus Bronsted and Thomas Martin Lowry each independently proposed that Arrhenius' definition of a base had to be modified. They both proposed that bases be defined not as hydroxide donors, but as proton acceptors, compounds which can bond to protons and remove them from solution. Of course, there are multiple ways to categorize acids and bases, but we're going to focus primarily on just two of those. We're going to start with the more basic definition known as the Arrhenius definition. In an Arrhenius definition, an acid is simply anything that can break apart or ionize to form an H+ and some kind of additional molecule or ion that it leaves behind. Examples of these would include HCl, which provides protons and chloride ions, or nitric acid, which again comes apart to form protons and nitrate ions. Under the Arrhenius definition of a base is anything that dissociates in solution to form hydroxide ions. Hydroxide ions are these OHs here with a negative charge. So if a molecule directly dissociates to form OH-, it can be considered an Arrhenius base. And a classic example of this are the components of Li, sodium hydroxide and potassium hydroxide, which dissociate to form OH-. But there's a slightly better definition here for us to work with because there are a number of materials which, when added to water, have basic properties, but they don't actually carry hydroxide ions themselves. So we're going to switch to a different definition for the rest of this lecture. We're going to talk about what are called Bronsted-Lowry bases and acids. In Bronsted-Lowry definition, an acid is exactly the same as the Arrhenius definition is. It's got to be something that releases a proton. So again, HCl and HNO3 are perfect examples of Bronsted-Lowry acids. But a Bronsted-Lowry base is a little bit different. A Bronsted-Lowry base is a proton acceptor. It's some type of molecule or ion that, when in the presence of protons, as it is down here, will actually bond to that proton, scavenging it from solution. Now, the reason that we're able to do this is we're talking about aqueous solutions. And a Bronsted-Lowry base, when added to water, will take a proton away from the water, and the result of that is, of course, it leaves behind the balance, which is hydroxide ions. So Bronsted-Lowry bases, even though they don't have hydroxide ions directly attached to them, can create them via the water that they're being dissolved in. Examples of this would be things like carbonate ions, which take a proton to form bicarbonate and hydroxide, or ammonia, which reacts with water to form ammonium ion and that important hydroxide that makes it basic. Again, we're going to stick with those Bronsted-Lowry definitions for the remainder of the lecture. So we now understand how acids and bases do their work. According to Bronsted-Lowry theory, acids and bases are locked in a chemical dance, one releasing protons into solution and the other scavenging them. But our previous lectures on equilibrium have to have you wondering if that concept applies to acid-base chemistry. And of course it does. Anytime an acid releases a proton, it dissociates to produce not just protons, but a second piece of that acid, which is essentially the acid minus a proton. When a base picks up a proton, naturally it creates a new material that is itself plus a proton. These processes sound like the exact reverse of one another, don't they? So, for any acid dissociation or base association, I can simply reverse the process and they start to look a lot like their alter ego. Acid dissociation reactions like base association reactions and vice versa. Now, clearly, there's a special relationship between acids and the material that they become when deprived of a proton. And similarly, a relationship exists between bases and their association reaction product with an extra proton. So let's explore that a little bit more with the help of some illustration. Remember that a Bronsted-Lowry acid is any compound, we're calling this one HA, which dissociates to form protons and something else. In this case, an A- ion. Now, if you look at that reaction very carefully, the reverse of that reaction is actually a Bronsted-Lowry base, right? A- picking up a proton would cause HA to form. So there's a special relationship here between these two, the HA and the A-. We call these conjugate acids and bases of one another. This is a definition that many students struggle with. To be a conjugate acid or base is to be a part of a pair. It's not an absolute term. So HA is not a conjugate acid in general. It's a conjugate acid of A-, much the way that you would be a brother or sister of a person, but not one in general to everyone. So we can reverse the reaction to see this a little bit better. Here we have A- picking up a proton to form HA, and again we can see that relationship between the conjugate acid and the conjugate base of the two. The easiest way to identify conjugate acids and bases is to simply look for the difference of an H+, one proton and one unit of charge. When you see two species which differ only by a proton, they are, by definition, conjugate acids and bases. Let's consider a few examples here. Remember, they've got to differ by just a proton. So what that means is, for example, hydrochloric acid and chloride ion would be a conjugate acid and base. In the case of nitric acid, that nitrate ion would be its conjugate base. If we look at bases instead, we'll see the exact same relationship. Our base ammonia picks up a proton and changes by only a hydrogen and a unit of charge to form ammonium ion, its conjugate acid. And carbonate, our other Bronsted-Lowry base that we've discussed so far, forms bicarbonate, which itself would be the conjugate acid of carbonate. Now that we're able to identify conjugate acids and bases, we're going to put that little bit of information in our pocket for a while. I promise we're going to return to it. But for now, let's turn our attention away from conjugate acids and bases and toward the third player in the Bronsted-Lowry acid-base dance, proton itself. Let's start by thinking about the simplest class of Bronsted-Lowry acids we can, what we call strong acids. Those are hydrochloric, hydrobromic, hydroiodic, nitric, sulfuric, and perchloric acids. These acids have exceedingly weak bonds to their acidic hydrogens and will dissociate completely when added to water. This makes them relatively easy to model from a chemical standpoint. 1 mole of acid molecules in solution will produce 1 mole of protons. It was realized very early on that acid solutions can have differing levels of acidity. You put just a few drops of hydrochloric acid into water and a weakly acidic solution results, one so benign that it can be consumed by a human being. Just take my word on this one though, okay? Please don't try that one at home. Now add even more hydrochloric acid and consequently more hydrogen ions, and you get products often used to etch marble or pickle steel. Clearly, the strength of an acid solution, or its concentration, is critical to its usefulness. In 1909, no one understood this better than Søren Sørensen, a researcher at the Carlsberg Laboratory in Copenhagen. Sørensen had taken an interest in the chemistry of proteins, large complex biomolecules with potent chemical activity. And he noted that just how acidic a solution was seemed to often have a profound effect on the chemical properties of these complex biomolecules when they were dissolved in it. So Sørensen decided that he needed a concrete numerical method for conveying just how acidic or basic a solution was. This way, he could maintain proper scientific controls in his experiments on proteins. He did this by creating a new scale based on the total concentration of hydrogen ions in the solution. But just indicating the concentration of acid or base was cumbersome. So Sørensen wanted something more efficient. The product of his labor is a scale commonly called the pH scale. Let's take a look at that pH scale a little bit closer. Here's our generic acid dissociating to form protons and its conjugate base. Now, let's think about the concentration of those protons and the types of materials that would create them. And I'm going to do this with a little spectrum background here that we typically use, showing the acids in red and the more basic things in blue. So here are some regular household chemicals that you probably see or come in contact with a lot of the time. Way down here, we have the most acidic things like battery acid, vinegar, and lemon juice. And up here are some very, very low acidity compounds like drain cleaner, bleach, and ammonia. Now, what makes something acidic or not so acidic? Well, it's the concentration of the protons in there. So if we were to look at the proton concentration of all of these materials, all the way from drain cleaner down to battery acid, we would see a broad range of concentrations, right? All the way from 1 molar to 10 to the minus 14 molar. And we can write those out, of course, in scientific notation. That takes a little bit of the edge off of these gigantic numbers that we don't really want to have to cope with. But there's an even simpler way to do this. Look carefully at the exponents. The exponents themselves make a nice, simple system, right? It's just 14 numbers, right? Or 14 orders of magnitude that we span. So if we use those exponents and instead refer to the strength of an acid by the order of magnitude on which its proton concentration lies, we get a much more usable range to deal with, essentially 0 through 14. And this is the core of the pH scale. But that leaves a question unanswered. Drain cleaner has a proton concentration of 10 to the minus 14th molar, vanishingly small. And yet, drain cleaner is not the kind of thing you want to come into contact with because it's very reactive. It's very dangerous stuff. But it couldn't possibly be because of the proton concentration, could it? There's hardly any in there. So what's going on here? Why is it that the most dilute of the solutions here are some of the most dangerous that we don't want to come into contact with? Now, to answer our question, we have to investigate something called the autoionization of water. And that is this reaction right here, in which water itself dissociates into a proton and a hydroxide ion. Now, this reaction happens on a relatively small extent in pure water. In fact, it's an equilibrium, and its equilibrium constant is about 10 to the minus 14. Depending on temperature, it varies slightly, but around room temperature, it's about 10 to the minus 14. We call this very special equilibrium constant Kw to distinguish it from all other equilibria because it's so important to us that we understand it. Now let me show you exactly what Kw predicts for us. Predicts that the proton concentration and hydroxide concentration must always multiply together to equal 10 to the minus 14 in an aqueous solution. And what does that mean from a pH perspective? Let's take the negative log of both sides and apply what we know about our rules of logarithms to get this expression here. The negative log of proton concentration plus the negative log of hydroxide equals the negative log of 10 to the minus 14. Do a little simplification here. We find that the pH of a solution plus the pOH of a solution must equal 14. In other words, the hydroxide ion concentration is going to change proportionally with the proton concentration in any given aqueous solution. Now let's go back and look at our pH scale again, remembering that the OH minus concentration has to balance out Kw. So in the presence of this vanishingly small proton concentration, what does water do? It creates an enormous amount of hydroxide. So the hydroxide concentrations of these common materials reflects those proton concentrations. That, my friends, is a concentration of hydroxide that you don't want to be in contact with. And that is why chemicals like drain cleaner and bleach need to be handled with the utmost care. Because their very, very low proton concentration means they have a very, very high hydroxide ion concentration. And sometimes, when it's convenient to us, we use a similar scale to the pH scale called pOH, which we just saw in the previous slide. Again, notice that pOH always adds with pH to form 14 because of that autoionization of water dictating the behavior of aqueous solutions. So what this means for us is that when we want to express the relative acidity or basicity of a solution, we have options. We can use, for example, the pH. We can use the proton concentration itself. We could also use the hydroxide ion concentration, or what we call the pOH. And all four of these expressions are interrelated through Kw and the log function that was used to first produce the pH scale. So if you were to be given any one of these four values and instead wanted to know one of the others, we could simply follow any route that we like around this box to find out what the pOH or pH or H plus or OH minus concentrations would be. So Sorensen had created for himself a useful, compact numerical scale for the reporting of acidity. He used the now familiar notation pH as a shorthand for power of hydrogen, since the pH scale itself is based on the exponent in the hydrogen ion concentration. What he may not have realized at the time was that the entire world would soon adopt his system, and that more than 100 years later it would still be the standard method for reporting acidity and basicity of materials. It makes such a useful standard because in combination with our understanding of Kw, the autoionization of water, and logarithms, pH can be quickly converted into a host of other useful units to solve a range of chemical problems. So let's summarize our discussion for today. We started with ancient Greece, where sour-tasting materials were grouped into a class of compounds called acids, and slippery-feeling materials were lumped into a class called alkali or bases. Next, we took a look at more modern chemical attempts to define acids and bases. We saw how Lavoisier's failed attempt to explain acidity with oxygen led to this element's name, and how only after oxygen's name had become widely accepted did Humphrey Davy demonstrate that oxygen was not essential for acidity at all. We then considered how Svante Arrhenius' theories on ionization led him to correctly classify acids as proton donors in solution and bases as hydroxide ion donors in solution. And our final consideration toward determining acids and bases came from Bronsted and Lowry, in which solvent participation is considered, and an acid is defined as a proton donor and a base as a proton acceptor. We saw how Bronsted-Lowry theory results in the formation of conjugate acids and bases, and how the stability of a compound's conjugate base can be used to predict if it will behave as an acid when dissolved. Finally, we joined the lab of Søren Sørensen, who felt the need to create a convenient numerical scale which could communicate concentrations over many orders of magnitude using simple, easily digestible numbers. This, of course, led to the pH scale that we know today. We've accomplished a great deal today. We've defined what acids and bases are and how we can begin to communicate their concentrations. But our work is far from done. Today we confined our discussion to acids that ionize completely in solution, those known as strong acids. The truth is that precious few acids ionize completely like this. Most, like many of those found in foods, drugs, and other useful materials, only ionize partially. We'll begin to tackle this idea next time. I'll see you then.